Hello, class. I thought that I would do another lecture. This is basically going to just finish up some things that I wanted to do for the last lecture. Turn the timer on this time. And also to talk about vectors. Start to get into just a review for many of you in vectors and how vectors work and cross products and dot products and what they are and everything else. All right. So trying to get all of my pens and things organized here. All right, let's go back to the tablet. There we go. Focus in there, Mr. Tablet. All right, so last time, I just want to sort of write some equations down here that we're using all the time now. Coulomb's force is going to be Q1 times Q2 divided by 4 pi epsilon r squared. Everybody's got that. And then we also know that, and of course those units are going to be newtons. And then we also know that we've got the electric field. Now that is a force field, so we'll put a vector sign over the top of it. And then we also know that we have an electric field equation, right? And the electric field equation is for the field for a or what the force a 1 Coulomb particle would feel at that point in an electric field, right? So let's just look at that. And of course, this is going to be in newtons per Coulomb, right? So we've got Q, which is the candidate particle that we're finding out the electric field for, and that's over 4 pi epsilon r squared, right? Okay, and of course, because we've now divided the force equation by a Coulomb, what we have is newtons per Coulomb. Remind me never to write up here on the top of this again. I don't think I've got it. I should have given myself one more line, I guess. So that's our electric field. Now, I want to talk a little bit about electric fields, right? And here's the thing. Let's look at something like this. Let's say that I have a printed circuit board, right? A printed circuit board, not a low frequency printed circuit board, but a printed circuit board that goes in your cell phone. And so let's just look at what I would have there. So I've got, I'm going to draw this in well, be sort of three-dimensional, but I certainly don't think that it's going to be a perspective drawing, right? But I'll try and do it. Ooh, look at that, pretty close to perspective. Now, let's say that I have down here on the bottom, I've placed a ground plane, right? And that ground plane, I've solder waved that over the entire bottom. So the entire bottom of this epoxy, right? Because this is a printed circuit board. So the middle of it is going to be epoxy. That's what printed circuit boards are made out of. And so I've now coated the bottom with copper. So I've got a copper ground plane here, and then I actually ground the bottom of it so that we know that the bottom's voltage is going to be 0 volts, right? And then on top, let's say that I have a trace. Now I'm just looking at one part of the board, obviously, but let's say that I have a trace, a conductive trace that is going on top of the board, right? Made of some type of copper, and we've etched it out on the top of the board, right? Does everybody see what I've got here? That's a copper trace, so a very conductive copper trace right on top of that board. And let's say that that copper trace up there is not 0 volts, but it's 5 volts, right? In fact, you're saying, hey, that sort of looks like it could be a capacitor because I've got 0 volts down here and I've got 5 volts up here. So that means that's like a capacitor. In fact, I can blow up this area that we've got right here. Let's just take that over here and blow that up a little bit. So what I would have is I would have on top 5 volts. And on bottom, I'm going to have 0 volts. Okay? Now, let's just say that these are the sides here. I'll just bring this down. That's the side, and I don't know, I'll bring that out a little bit, and I can say that that's the side over there. All right? Now, how are the electric field lines drawn? All right, this is something I want to put up here too. Electric field lines. And how do I draw? What are the rules of thumb for electric field lines? Electric field lines are just like current lines. They always go from positive to negative. That's their direction. Their direction is from positive to negative. And there is some fringing that can occur. I mean, if we're going to extend this ground plane, let's say that's a trace line on the top of a printed circuit board, but the whole bottom of the printed circuit board is 0 volts. Let's say that. How would I draw my electric field lines? Well, I think that everybody can see how I would draw my electric field lines right in the middle here, right? So it would just be like that. Does everyone see that as red? Oh my God, it is red. It's fantastic. So I'm using a red pen. So there you go. My electric field lines would be from the 5 volts to 0 volts. I think everybody can see how that would go on the inside of that trace. How would it go around the fringes of that trace? How would it go around the fringes of that trace? Well, here's the rule of thumb, right? An electric field line, so an electric field line, I'm not just going to use the abbreviation, an electric field line always, let's underline that, enters a conductor perpendicularly. Now, of course, that's not drawn perpendicularly. Why didn't I draw that? You know, I'm drawing everything. I'm writing fast. Anyway, it's perpendicular. Where's my? All right. If you're going to be picky about it, it's perpendicular. See, now you're not going to forget it, are you? You see how this is entering perpendicular to that? So the electric field line exits a conductor and enters a conductor perpendicularly. And you're saying, well, it makes pretty good sense here. Well, there's other geometries in which it won't be so obvious. And now let's look at the outside here and how it exits this. Come on, I'm trying to tap this thing to get it to come in Focus. It wasn't focus. Get in focus there. I might have to do the old reset on it here. Here's my reset. Hi, how's it going? Once I come back to this camera, then the other one autofocuses when I go back to it. There you go. Much better now. I've tried to shore up the table and everything. I'll try not to move too much. So when you get out here at the end, you find that the thing tends to fringe like this. See, it's still entering the base perpendicularly, and in fact, it's leaving the thing perpendicular, the top strip. Well, not on this one. That should have probably gone more like that, but perpendicularly too. Now, these two fringing areas that you have out here are significant. And when we get around to analyzing microstrip transmission lines, which is later in the course, this will pop up. And that's what we're looking at right here. And that is what is happening inside your phone. So don't think that as an electrical engineer, you're never going to work with microstrip transmission lines, right? And now, there is a good question about that. Does, your phone is so small, does it really matter if there's attenuation over the trace lines inside your phone? By the way, inside your phone, those trace lines, right, like this, if they're high frequency trace lines, they have to be the geometry of the width of the trace, the thickness of the printed circuit board, all have to fall within the design so that the characteristic impedance, you have to match the characteristic impedance at high frequency, radio frequency, and that's a lot of stuff that's going on inside your phone. You have to match the impedance of this with the impedance of all of the other communication devices within the printed circuit board on your phone. So don't think that your printed circuit board on your phone does not have coaxial cables. It does. It's just that they're called microstrip transmission lines on the printed circuit board inside your phone. And when we're looking at coaxial cables later on in Chapter 8, the chapter on transmission lines, we're also going to be looking at microstrip transmission lines and how that changes in those two. And the real change there is that you have such high frequency, and frequency does, I'm going to let the cat out of the bag. There's so many, the cats, cat out of the bag. What was the cat doing in the bag? I don't know. Anyway, I let the cat out of the bag now. There is attenuation, and attenuation along the transmission line, whether it's a transmission line like a microstrip transmission line, a coaxial transmission line, a high tension power transmission line, all of those are frequency driven as far as the attenuation goes. And that's why we have 60 hertz power. See how all of these questions are being answered that you actually forgot to ask yourself your whole life when you wanted to be an electrical engineer, and now you just realize, oh my God, I should have asked myself that question a long time ago. All right, let's go on. So if we look at this again, let's expand this. I just wanted to show you the electric field lines. Let's take a second here, because we are talking about electric field lines. Let's place that up there at the top of our topic, subject list in our topic for the lecture today. With electric field lines, let's look at another geometry of electric field lines that we're going to be looking at quite a bit throughout the semester. So why not do it now? Now, what I'm going to do is I'm going to exaggerate the size just so that I can draw the radius of the signal wire inside the coaxial cable, right? So obviously the signal wire inside the coaxial cable is not that large, right? But I did that just so I could draw a radius there and also draw a radius here. And so this radius is B, and this radius right inside here is A. I hope you can see that, but the A is very small. It's right there. So the radius of the signal wire is A, and the radius of the outside, let me draw that copper braid that we have. When I say copper, I meant aluminum braid that we have around the outside of a coaxial cable, right? So that's what a coaxial cable looks like. It's got a signal wire, which is round, cylindrical, that travels the entire length of the coaxial cable, right? And then around the outside, you have a aluminum braid, right? It's braid. You know that I just drew on there with red for. Now, you've got this. This is 0 volts. Now, the signal wire on the inside of the coaxial cable, just like this one up here, you know, when I'm talking about the signal wire, I'm talking about digital transmission rates, and 5 volts is what this is part of the time, and 0 volts is what this is part of the time if they're using regular 0 and 5 volt TTL voltage levels in the transmission that they're using at radio frequency inside this printed circuit board. All right? I hope everybody got that. Now, over here, I've got 0 volts on the outside, and what I've got on the inside signal wire, if we look at it, is a waveform that is varying, right? And it's varying at radio frequency. When I say radio frequency, I'm talking about anywhere from 100 kilohertz. In fact, I'm going to look it up right now, and I'll tell you what radio frequency would be. Probably from about 1 hertz, it says, all the way up to 10 gigahertz. But that's not what I would call it. I'd really call it in the kilohertz range, anything from 10 kilohertz all the way up to, you know, into the megahertz range, 100 megahertz or whatever is radio frequency. I probably should look at the exact definition of radio frequency before I say that, but that's not what this lecture is about. We've got radio frequency. All I'm saying is that it's got an amplitude, right? It's got a positive amplitude and it's got a negative amplitude here. So we've got electric fields oscillating inside here. When this has a higher voltage, I draw my electric field out like this, don't I? So that's the one that I'm going to draw. I'm going to focus on drawing this electric field when it's right at the maximum, right there. What would that look like right here? Let's say it's 10 volts. It's not, but let's say it's 10 volts, and the outer ground shield is 0 volts. So I've got a large electric field there. But look at the geometry of that electric field. Am I still leaving the center conductor, the signal conductor, at 90 degrees? I'll try and pick one where I am. Yes, I am. See right there. That's probably the only one I drew that was actually at 90 degrees. And then out here, I've got another one at 90 degrees too, don't I? So do you see how this also coincides to what I've done here, 90 degrees entrance there, and at the same time 90-degree exit from the conductor up there, right? And I'm saying, you know, how would you draw? How would you draw with something? Now, these two, by the way, are very familiar, very common types of geometry where you would look at electric fields, right? Now, I want to point another thing out. I said that this was 5 volts and this is 0 volts. You know, let's blow that up a little bit. Let's just take that section right here, just the center section here. And let's blow that up over here. And I'm actually going to use, I'll put my trace up here, right? I'm going to extend the thing here, 1, 2, 3, 4, 5, and I'm going to say that my bottom conductive layer that's at 0 volts is down here. So up here I've got 5 volts and I've got 0. Right. So we've drawn our electric field lines, haven't we? Those electric field lines are drawn from the positive down to the lower voltage, in this case 0 volts. So those are electric field lines. Now, and we know that those are perpendicular, right, to both of the two, just like they were up here. Now let's draw our equipotential lines. Equipotential. I know you're learning so much so fast, and I've got Mount Everest for you to digest. So, I could go on just doing these lectures ad infinitum on electromagnetic waves, but we're not. We're just going to keep going. You're learning a lot. You're going to learn a lot more. You're going to learn a lot of the mathematics. But right now, we're trying to focus on the concepts of what an electric field is, concepts of electric field lines. Never forget that really the electric field is just a force field for a 1 coulomb charge. Remember that down there at the bottom it says newtons per coulomb. It's newtons per 1 coulomb. So all you have to do is think of the force field and think of Q2 as 1 coulomb, and it gives you the electric field, right? So anyway, let's get back to this. So what are our equipotential lines inside here? And what does that mean? That means equal voltage. Equal voltage lines. Where would my equal voltage lines be in here? We know that inside this, and we know that this is epoxy, right? Let's say that just like we've got up here, and I said that that was epoxy, or epoxy over here. This area in here is epoxy. Epoxy is a dielectric, I hope everybody knows, and just like air is a dielectric, mica, glass, most of these things that I'm saying, you're thinking, oh, those are insulators. Yeah, they're insulators, but they're also dielectrics, and dielectrics and insulators aren't necessarily the same, no. But you might say that dielectrics in many ways is a subset of insulators. Now, I've got my electric field lines going like that. Well, where's my equipotential lines? Well, that's 0 volts. Well, then isn't this right here 1 volt? Wouldn't this then be 2 volts and 3 volts and 4 volts? And then, of course, on the very top here, I've got my 5 volts again, don't I? That's a 3. That's a 3. So do you see what I mean by the equipotential lines, the lines of equal voltage? And I know another thing that you're thinking too. You're thinking, oh my goodness, those equipotential lines, they cross the electric field lines at 90 degrees. Everywhere. They always cross the field lines at 90 degrees. That's right. So if I was going to draw equipotential lines in here, right, where this is 10 volts on the inside, I'm just going to draw. Well, if it's 10 volts on the very inside of that signal line, then wouldn't halfway halfway from the inner signal line of that. I mean, that's just at this instant in time. Don't forget, remember, my x-axis here is time, right? And this is amplitude, or in this case, voltage. So what would be halfway here? I think everybody could see if that's 0 volts and the center is 10 volts, then that would be 5 volts, wouldn't it? Right? And that would be my equipotential line of 5 volts. Now, look at, does that equipotential line of 5 volts cross my electric field lines at 90 degrees? It sure does. And so you're probably thinking, this is too easy. God, this has got to be the easiest lecture I've ever seen. Let me show you a more complex geometry then. What if I had a geometry like this? I have a signal line here, and I have a ground line here, right? So this is my signal line. I'm just going to come down here to actually label it. So that's my signal line. I'll say that's 10 volts, right? 10 volts right there. And this, if we come down here, I'll say that this is 0 volts, right? They're long lines that are running, you know, 2 long electric lines. One electric line running like this, and then another, another electric line running like this over here, parallel. So they're 2 parallel electric lines. You know, for a second there, I probably just could have drawn it, those 2 parallel electric lines, but I thought I might have lost somebody, so I thought I'd draw that. Now, if I were to look at these 2 electric lines, what does my electric field look like? And in fact, what I'm going to do is I'm going to take these, right? This is the 2 electric lines that I've got. Now I want to look at them. I'm going to look at them from this angle, right straight down at that angle, just like I had them drawn originally, right? So let's just redraw them down here. There's still going to be 10 volts and 0 volts, but I'm just going to draw the 2 circles now, as if we were looking at them end on, like I've got my little eyeball looking at them right there, right? So what would my electric field look like? Well, it has to leave the positive conductor, right? It has to leave the positive conductor at 90 degrees, and it has to go into the ground conductor at 90 degrees too. So how about this? Right? I'm going to put a little arrow there because we know it's going in that, because we know that this is my positive and this is my negative, or my ground. Does everyone see that? I wonder if, I'm going to shake it a little bit. Yeah, I have no idea. Oh, that made it worse. Oh, well. Should whack, I feel like just whacking that camera that they gave me a cheap camera on purpose because they hate me so much. Now, that's one line. Let's do another line. How about this? It's that now that's coming out perpendicular, isn't it? Coming out perpendicular to the positive signal line, and it's going into that at 90 degrees as well. I could have drawn it a little better there. Let's do the same one on the bottom here. That's probably a little better. How about one of these coming out of the back, right? Oops, that's not too good. You see what I haven't drawn it too well there, obviously, but I think you get the general idea about how the electric field lines have to emanate from the positive conductor and go into the more negative conductor. So all of these have direction as well. Don't ever forget that electric fields are vectors. They are not scalars. They have direction. Oops. And then I draw it in the wrong direction. Right? So that is just, now you're probably thinking, well, where are the equipotential lines for that? Well, let's see. Here would be one equipotential line right down the center of that. Does everybody see that? Right down the center. All of those are perpendicular. Well, they're supposed to be perpendicular, drawn perpendicular to that line. So that would be an equipotential line. Now, what equipotential line would that be? This is 0 volts, that's 10 volts. So there would be my 5-volt line, wouldn't it? Does everyone see that? Now let's go, let's do another one. Well, we want to be perpendicular to this, but we've also got to be perpendicular. Let's just work with this line right here. What if I was perpendicular to that? I then had to be perpendicular. Oh God, let's not go this way. Let's go this way. Let's say that I come off perpendicular to that, and then I have to be perpendicular to that, and then I have to be perpendicular to that. So there's one, and then I would be coming down here perpendicular to that, perpendicular. Boy, I don't draw these too well, do I? And perpendicular to that, and then we can also find ones that are in the middle here. So my equipotential lines would look like the dotted lines on the sheet there. Actually, it comes up pretty good on the camera. I'm better than even on, well, yeah, whatever. So do you see the difference? These would be my equipotential lines, and that tells us where the voltages are exactly the same. So here's 5 volts. The one that I've got right in the middle there would be 2.5 volts. The one right in between that would be 3.75 volts. So you can see how I would draw my electric field lines with a variety of different points, and also how I would draw the other ones. Now, I want to just take the last couple minutes here to draw one that is atypical to all of these. This is power lines, right? And I think everybody can see power lines, coaxial cable, microstrip transmission lines. So we've really covered probably 3/4 of all of the different types of things that you would have. Let's just look at one more. What if I had something that was like this? Right? And I grounded this. I grounded the outside of that horn, or whatever it is, that box. And then inside the box, I had a triangular area, and that was my signal. And let's say that was 10 volts, right? So 10 volts there, 0 volts here. What would my electric field, my cross-sectional electric field, look like inside that coaxial cable, right? You know, coaxial cable, of course, is long cable like that. Let's say that this also is some type of cable, like that, right? Something like that, and then it's got this thing inside of it. What would the electric field look like? Well, I think what you're probably thinking is, well, this thing has to come off here, and then it's got to go someplace out here to be that. So let's start there. It's got to come off like that, right? And then it somehow has to go to, you know, someplace over here, right? This one has to come down that way, and this one has to come up this way, right? Now this one up here, where would that go? Well, all of these, right? All of these are coming out along here. This one along here, you know, there you're going to have one that's coming down like that too. So that's where all of these are coming out of. You would have one right at the end here that would probably go right up to that. If you wanted to, you know, draw that one, you could, right? Now, this has to somehow cover all of these areas. So I'm just going to draw one down here. I'm going to draw one down here. I'm going to draw this like this. Do you see what it is? You see how that it has spread out there? And you see how all of my lines are still, right? Perpendicular leaving, perpendicular going into the sides there. Sorry to take so much time here, but one time I didn't draw it all out, and then the students came up to me, and he was you know, he's like, well, I don't get it. Why does only one side go up? And I thought, well, no, you know, so I draw the whole thing now. And what you can see is that, at least in most cases, not in that one right there, that was probably a bad one, those go up. All right, that's the end of lecture, I guess, number 6. But actually, there's, with 0 and 0.5, there's 2 more. But that gives you an idea of, now, where would you draw the equipotential lines in there? I will let you think about that, right? Okay,